Good day, learners. Today we will discuss bisection method. This topic is composed of four different parts, such as definition, theorem, algorithm, and example for bisection method. Let's begin. To solve nonlinear equation, we can use bisection method. It uses the process of dividing repeatedly the interval, which is under bracketing method. It is known as binary search method and is also considered as one of the first numerical methods or solutions developed to find the root of a nonlinear equation having one unknown variable. Below are the following theorem where bisection method is based on. The figure 1 shows that XL and XU have opposite signs, which forms a bracket. The condition is that if the product of the function of XL and XU is less than 0, then there is at least one root that exists between XL and XU, given that the function of x is real, continuous, and changes sign. Next, we can observe on figure 2 and figure 3 that the sign of 2 points does not change. However, there may or may not be any root between XL and XU if the product of the function of XL and XU is greater than 0. Lastly, if the product of the function of XL and XU is less than 0 and changes sign between 2 points, more than one root may exist. Now, let's proceed on the algorithm of bisection method. Step 1. Choose XL and XU as two guesses for the root such that the product of function of XL and XU is less than 0, or in other words, function of x changes sign between XL and XU. Next, estimate the root or xm of the equation function of x is equal to 0 as the midpoint between XL and XU, as xm is equal to the sum of XL and XU divided by 2, or the average of XL and XU. For step 3, we have to check the following. A. If the product of the function of XL and XM is less than 0, then the root lies between XL and XM. Then XL will remain XL in the next iteration, and XM will be the new XU. However, if it is the greater than 0, then the root lies between XM and XU. XM will be the new XL, and XU will remain as it is in the next iteration. Lastly, if the product is equal to 0, you will stop solving because the root is XM. For step 4, it is to find the estimate of the root by solving the average of XL and XU, followed by computing for the absolute relative approximate error by getting the absolute of difference of the estimated error from the present iteration and estimated root from previous iteration, divided by the estimated root from present iteration, and then multiplied by 100. The final step is to compare the absolute relative approximate error with the pre-specified relative error tolerance. If the absolute relative approximate error is greater than the pre-specified relative error tolerance, then go to step 3, else stop the algorithm. Note that one should also check whether the number of iterations is more than the maximum number of iterations allowed. If so, one needs to terminate the algorithm and notify the user about it. And to understand well the bisection method, we will be having an example. The problem is to find the root of function of x equal to x cubed plus 3x squared minus 2x minus 1, using the initial guess of xl is equal to negative 3.8 and xu is equals to negative 1.2, and the pre-specified tolerance of is 0.001%. We will be using an Excel for this method. Here's our worksheet to solve the problem. We have here a table consists of columns for the number of iterations, XL, XM, XU, f of XL, f of XM, and f of XU, and lastly is for the absolute relative approximate error. Let's try to have 20 iterations. 1, 2, let's just put it here. Now, let's check the steps. Step 1 is to choose the XL and XU that is less than 1. The given is less than 1, so let's type them such as negative 3.8 for XL, and for XU is negative 1.2. Next, step 2 is to estimate the root xm, or the function of f of x is equal to 0 as the midpoint lies between xl and xu. So our xm will be equal to xl plus xm divided by 2. Next, the f of xl can be solved by substituting the value of xl in the given equation. We'll substitute this. It's equal to then plus 3x squared plus 3 times square root of this xl, then minus 2 xl minus 1. Then we have an answer of negative 4.9520. And the same process goes for f of xm and f of xu. Let's do it again. Equal cube plus 3 times square root of this minus 2 minus 1. Same process for f of xu. Let's change it into f. Then, the absolute relative approximate error on iteration 1 is 0 since we don't have yet a value for the previous iteration. Let's put 0. Next, on iteration 2, we will follow step 3. Let's check the product of f of xl and f of xm. The value of our solved f of xl is negative, this, and while f of xm is positive. So their product will be negative or less than 1. If we multiply them, let's follow the condition. So the condition here is if f of xl times f of xm is less than 0, then the root lies between xl and xm. So xl will remain xl and xm will be the new xu. We'll just have to pull this one and pull down. We will have a negative 3.1500 for xm, and we also have to pull down the columns for f of xl, f of xm, and f of xu. We will now have a value for the absolute relative approximate error on second iteration by using the equation of step 4, which is the absolute of the difference of the estimated root from the present iteration and estimated root from previous iteration divided by the estimate root from present iteration and multiplied by 100. Let's type the function. It's equal to absolute of minus the previous iteration divided by the present iteration, the xm of the present iteration, times 100. Enter. We have here 20.6349. For step 1, we have to compare the absolute relative approximate error with the pre-specified relative error tolerance. We have 20.6349, which is greater than the pre-specified relative error tolerance. With that, you have to continue solving. For iteration 3, the product of f of xl and f of xm is also negative. Therefore, xl will still be the xl and xu is the xm from the previous iteration. Then pull this down as well as the other columns. For iteration number 4, the product of f of xl and of f of xm is still negative. Therefore, xl will still be the xl and xu is the previous xm. Then pull this down as well as the following columns. Next, the product of f of xl and f of xm in the fourth iteration will be positive because negative times negative is positive. With that, we will follow the second condition that if f of xl and f of xm is greater than 0, then the root lies between xm and xu. Then the xl will be the previous xm, this one, and for xu, it will remain xu. And pull this one again, as well as the other columns. Another way for us to do this one by one is using the formula, the if formula and the XL. For XL, we will type equals if of f of xl or times f of xm is less than 0, then xl xm. Let's try this. If xl times f of xm is less than 0, then xl xm. Then enter. It is a command to make xl stays the same and xm will be xu if the product is less than 0, and if it not satisfies the condition, the system will do the opposite way. For xu, type equals if f of xu times f of xm is less than 0, then xu sm. It will make them xm to be xl and xu to remain the same. Let's type the formula. Equal if f of xu times f of xm is less than 0, then xu xm. Enter. Pull this down as well as the other columns. Now we have formula. We can freely pull all of this until our 20th iteration. Now we already solved the 20 iterations that we aimed a while ago. Let's check our step 5. We have to compare the absolute relative approximate error with the pre-specified relative error tolerance. If it is greater than, then we have to go back to step 3. As we can see, the iterations from 1 to 16 are all greater than with the pre-specified relative error tolerance. And for our 17th iteration, it is less than the pre-specified relative tolerance error. We have to check on our step 3. If it is less than we will proceed, and if it's greater than, we still need to proceed on the iteration, and if the product of f of xl and f of xm is equal to 0, then we have to stop the algorithm. As we can see, here are the list of our f of xl and f of xm. Let's highlight it. From here, we can notice that multiplying f of xl and f of xm from iteration 1 up until iteration number 18 are all greater than 1. And for our 19th iteration, f of xl and f of xm is equal to 0. Therefore, from here, we can conclude that our xm, or the root, will now be negative 3.4909 here. This one because the product of f of xl and f of xm is equal to 0, and that ends our computation. It also says that our absolute relative approximate error is less than our pre-specified relative error tolerance. We have our EA is this one. And it is less than our pre-specified tolerance, which is 0.001%. And to solve other nonlinear equations that can use bisection method, you can repeat all the processes that we do in our example. And that will be all. Thank you for listening.